Good afternoon, everyone, and thank you so much for joining us for another round of bite-sized corrosion discussions. So for those of you who don't know me, my name is Vanessa Seeley-Fisher, and I'm a director at Isiniti and involved with Isifundi training. Today is going to be a first discussion into material selection, and it'll be the first of a 2-week series this time. For a lunchtime chat really about some issues on materials. Most importantly, I want to say thank you for taking time out of your day today to join us as we do delve into another corrosion conversation, which we hope you will find valuable and that it might help clarify some concerns for you or set you on a path to ask questions in your own circumstances. Neil Webb is back in the hot seat this week. As a metallurgical engineer, he has a comprehensive understanding of materials, of construction, and of course his 40 or so years in the corrosion sector has suitably supplemented that from a corrosion perspective. So Neil, over to you as you talk about material selection.
Thank you, Vanessa. So today we are going to talk about material selection for corrosion protection. And there's a very pertinent saying in Afrikaans, Goedkoop is Duurkoop. In other words, you make your choices and you live with consequences. And sometimes those consequences are not exactly what one would desire. Now, this is such a vast field that it is impossible to cover all the aspects of material selection in just 20 minutes or so. And so what I thought I'd do is talk about some of the things that we have to take into consideration when we select materials, and then illustrate some of the things that can go wrong when we've made some choices. Of course, the most important consideration when we start is what are the operating conditions? And usually that is perhaps the most important, although sometimes if we only consider the operating conditions, we'll end up being caught short. And that is because operating conditions are the norm and life is not always normal. Sometimes things go wrong. So what happens when there is an upset condition? We need to think about what can go wrong in the process that we're involved in that can change the conditions that we are in fact subjecting our structure or our plant or whatever it is. What are those conditions that we're subjecting it to? How can they change? And what effect is that change going to have? And then, of course, we're all human and people can make mistakes. We can overlook things. We can make choices based on previous experiences, and perhaps those may not be the best. So let's have a look at some of these aspects. In operating conditions, perhaps the most important thing is how long do you want this thing to last? You know, you can make something out of 12 millimeter thick plate and it'll last for 200 years. If you only need it to last for 5 years, why make it out of 12 millimeter plate if that plate is going to corrode away? You may have other aspects such as strength and so on, which may determine that 12 millimeter plate is necessary. But then you need to know that that 12 millimeter plate is going to last for the entire life. If it corrodes away at 1 millimeter per year, in a couple of years' time, it's going to be unserviceable. Temperature is a huge aspect to consider. Things that work well at ambient temperatures do not necessarily work well at high temperatures. Those high temperatures can be temperatures that we just experience out in the environment. Leave something out in the sun in the Northwest Transvaal, and you find that the temperature will go up to 60 or 70 degrees. And not all the materials perform well at those sort of temperatures. You may well design something for flow conditions, but what if that flow condition includes abrasive materials that wear away the coating that we are looking at, for example? Sometimes just velocity can cause a problem. How fast is the liquid moving in a pipeline, for example? So many water pipelines are designed with a flow rate of something like 2 meters per second. What happens if you suddenly put in a constrictor, or if you have an elbow and the velocity increases significantly? Is it going to change the expected life of that material? And perhaps one needs to then put a different material of construction in place to handle those conditions. And then, of course, there's chemistry. Corrosion is a surface phenomenon, and it is the interaction between the material and its environment that we are involved in. If that environment then changes, if it changes from, say, a neutral pH to a pH of 3, you think, well, from 7 to 3, that's only 4 digits, but actually the pH scale is logarithmic. So going from pH 7 to pH 3 is not 4 times, it's 10 to the power 4 times the concentration of the acid. And that change in concentration, be it acid or alkali or a salt or whatever, can cause significant differences in the behavior of a material that has been selected. Is the process that we're dealing with constant, or is it cyclical? In other words, does it change? Does it go up and down on a regular basis? Perhaps one of the most common examples of that is vibration, which we've listed down below. If something is vibrating, it is far more likely to fail than if it is a steady stress. Is the infrastructure subject to electrical interferences? Sometimes if you superimpose an electrical interference over the top of a chemical process, you get surprising results. And we actually saw that when we were talking about cathodic protection and the disastrous effect that stray electric currents can have on our corrosion reactions. If you put a component under stress, generally it will corrode faster. So we need to consider those aspects as well. Here's a photograph of a material that was selected based on chemistry and temperature. And as you can see, although there's some slight discoloration of the weld compared to the rest of the material, it has performed pretty well. But what wasn't taken into consideration in this particular case was erosion. And the net result was significant erosion corrosion on the tips of the impeller due to the abrasive nature of the slurry that was being agitated. What about upset conditions? Perhaps one of the most common upset conditions is temperature. I remember a situation where we were called on to design a protection system for a bottle washer, and we had a very short period of time in which to do this work during a shutdown. And so the material that was selected was one that could take the temperature that we were given as a design factor and could be applied quickly and would cure. About, a few weeks after the bottle washer had been put back into operation, we got a panic phone call from the operator that the coating was coming out in sheets and contaminating the bottles. So we went and had a look at this, and the coating had all the appearance of having been cooked. So we said, well, what is the temperature? No, here's the temperature. It was 55 degrees C or thereabouts, if I remember correctly. And he said, well, this coating has been subjected to much more than 55 degrees C. He said, no, that's impossible. If we exceed 55 degrees C, we're going to ruin the product. So we put some temperature recorders in this bottle washer, and guess what? During the night shift, the environment went up to 80 degrees C, not exactly what had been designed for. So we need to be very, very aware of upset conditions. These upsets can be in temperature, they can be in pressure, they can be in stress, they can be in the environment. If you design something for or select a material for something for a particular environment and then expose it to something else, don't be surprised if it doesn't work very well. And those environments can either be atmospheric environments or process environments. There was an incident where a coating system was selected for an indoor temperature-controlled, humidity-controlled environment, but during construction, the structure was exposed to sea air, the wind blowing directly off the sea, the structure being located very, very close to the sea. And the net result was, before the structure was even completed, the coating had failed because it was not designed for that particular environment. Here's an interesting and slightly unusual example of an upset condition. Those rods that you can see in that box are actually silicon ion anodes that are used for cathodic protection. And these were selected for their long life in the environment in which they were going to be used. So they were packed in straw and sent in a nice strong wooden box. The only problem was that whoever was handling this didn't realize that the contents were actually relatively fragile. And silicon ion anodes, if you drop them, they break. So our wonderful anodes were perfectly suited to the environment in which they were intended to be used, but totally unsuited to being transported in a wooden box. Here's an example of a situation where a structure was designed for a particular environment, and due to fallout from an adjacent process, the structure was contaminated with highly aggressive salts, and the net result was serious corrosion of the reinforcing. Here's an interesting example of a chimney on a boiler. The materials was selected for its strength. It was considered to be non-corrosive inside the chimney because the design of the chimney was such that the temperature would be above the dew point. And in spite of the fact that the boiler was using a fairly high sulfur content fuel oil, the situation was considered acceptable because the gases, in theory, were not going to condense. However, what happened here is that the cooling effect of these sections that were then welded onto the shell of this chimney caused those areas to be cooler than the rest of the structure, and therefore you got dew point conditions on the inside of the stack at these points. And when you look at the stack from the inside, you wonder that it actually was still standing at the time that they took it down. We are human, as I've said, and there are a lot of things that can go wrong. Ignorance, if you'd never got told about something, how can you design for it? One of the most important aspects of professionals is that they undertake a code of ethics that says that they will not do something that they are not qualified to actually design. Unfortunately, many engineers step outside of those parameters. It could be negligence, not thinking about something. The people involved could be under stress or pressure. It could be personal stress. It could be pressure of a deadline. You can be doing it in a hurry. Oh, I'll just quickly use that specification. And there's a very well-known saying, if you think it's expensive to hire a professional, wait until you hire an amateur. And that is not an immediate expense. It's something that comes later. So in terms of our corrosion situation, we can select materials of construction, such as in a seawater cooling system. What are you going to make those pipes and valves out of? Carbon steel, stainless steel, non-ferrous metals. We can select coating materials. What am I going to coat my structure with in order to stand up to the environment for the length of time? There is a bewildering array of coating materials that is available. There are two-pack materials, there are single-pack materials, there are special materials that are kind of a combination of the single-pack and twin-pack materials. How on earth do you choose what to do, which one to use? Well, we're going to be giving a series on coating selection in the near future. In the cathodic protection industry, we can select different anode materials. Are they going to be made of zinc or magnesium or aluminium? Or if we're using impressed current, do I use lead silver anodes or activated titanium anodes or platinum anodes or silicon ion anodes? Here's a good example of perhaps an incorrect anode selection because of the conditions to which it was exposed. You can actually clearly see the casting lines of these zinc anodes. And this is 5 years after they had been installed, and they've been permanently immersed for 5 years. And as you can see, they have hardly worked. So this is an example of an incorrect material selection. So let's quickly just run through some consequences of choice. I think that is the best way to describe it. In terms of our materials of construction, our choices will affect wall thickness and corrosion allowance. If you were, for example, selecting a material for a sheet pile for a harbor, you cannot use a corrosion allowance on the wall thickness if it is being subjected to what's known as advanced low water corrosion, because that's a pitting corrosion phenomenon, and wall thickness has virtually nothing to do with it. We might decide to use corrosion-resistant alloys, CRAs as they are known, or non-ferrous materials, for example, in that seawater cooling system. And there's a whole host of polymers and composites that are now becoming available, which give us good corrosion resistance. But then what about the mechanical properties? We mustn't forget those. Here's that seawater cooling system. And this is a very dramatic consequence of choice. Here you can see one of the valves, and it is starting to leak and is about to burst. Its companion valve, in fact, did burst, flooded the engine compartment and crippled the ship in the middle of the Indian Ocean. That's what the inside of the valve looked like. And that's not a photoshopped image. That is the true color. This valve was made out of cast iron and had been put inside a cooling system that was made out of copper nickel. And the copper nickel that plated out on the inside of that valve set up a bimetallic corrosion reaction, and the net result was a failed valve. Here's an example of internal corrosion where the wall thickness only just held. You can see the effect of the internal pressure where this particular pipe was on the point of rupture. Consequences of choice in coating materials. The cost of the coating material. Often people balk at the cost of the actual material, not realizing the material itself is a very small part of the overall cost of the system. You need to relate the cost to its service life, to its application. In other words, do a complete life cycle costing analysis in order to make the correct choice of material. Here's an example of a correct choice of material, say coating on a pipeline. And as you can see over here, the pipeline has been bedded in fine sand. Well, this worked extremely well. And after construction of this some 70-odd kilometer pipeline, there were only a handful of mechanical defects on the entire pipeline. So the next project that came along, they used the same material, but they didn't use the same sand padding. Due to the higher temperatures and the non-sifted backfill, this coating actually then was subject to penetration, and there you can see the hole left by a stone that had become embedded in the coating, setting up a coating defect. And this pipeline had literally hundreds of defects. Consequences of choice in anode materials. If you use the wrong anode material, perhaps the anode will corrode away by itself without doing any work. Perhaps it'll go to sleep, like that picture of the zinc anode that I showed you earlier. Maybe it will get consumed too quickly. Or if you use the anode in a saline environment, you may well land up with cable failure if you haven't used the correct anode cable insulation. You cannot use conventional cables in chloride environments like seawater or brackish water or brack soil even, because of the generation of chlorine gas. So here's an anode that corroded away by itself, never mind providing any protection. These anodes were used on an offshore structure, and there was a hasty decision made to merely continue the same principle of corrosion protection for the 2 kilometers of onshore pipe. Problem is, when you put an aluminium anode onshore without chlorides around, it goes to sleep. And that became, again, a very expensive, incorrect material selection. Vanessa showed us this wonderful valve. And a valve is a very, very good example of materials selection philosophy. Let's have a look at what a valve comprises. usually a cast iron body. The blade may be cast iron, which is coated, as was that photograph we've just seen. It could be a high chromium iron, it could be a stainless steel. The shaft generally is steel for strength. The bushers may be bronze, they may be Vesconite, they may be something else. The seal seat and the retaining ring are generally stainless steels. When you put all these together, you need to remember that there's this thing called the Galvanic series. And anything that is at the bottom of the series will corrode when it is coupled to something higher up. In that valve situation, if we had a steel shaft and a bronze bush, if those are exposed to the water, in other words, if the seals fail or if there are no seals, your steel shaft is then going to corrode inside or adjacent to the bronze bush. Here's a good example of a valve construction that was exposed for something like 20 odd years. And as you can see, there is a small amount of corrosion adjacent to this nut, but for the rest, it's in pretty good condition. Here, they got it wrong. They've got a stainless steel seal retaining ring and stainless steel cap screws, but they used steel washers. And you may say, well, where are the steel washers? Well, that's exactly the question. Where are they? Well, they've dissolved as a result of galvanic corrosion. So that stainless steel retaining ring is not being retained at all. Here's a similar situation. In this case, it led to an expensive failure of a valve, a $50,000 valve, because one of the main contributors was the incorrect nuts. There's the remains of the nuts that we picked up on the bottom of the pipe that used mixed up stainless steel and carbon steel nuts. Carbon steel nuts corroded away, and the net result was that failed seal retaining ring. So remember that down here, mild steel is anodic to cast iron. It's anodic to bronze. It's anodic to stainless steel. So we need to be very, very careful about our materials of construction. One of the ways of overcoming that issue is to, in fact, apply a material that is even more active than steel, such as one of the sacrificial anodes. And here's an example of a valve which we saw when we spoke about sacrificial anode protection, where the anodes have been welded onto the blade and they provide protection to the entire valve structure. And this valve, also after 20 odd years, is in excellent condition. So remember, guys, Goedkoop is Duurkoop. If you save a few rands at the outset due to choice of the wrong materials, it's going to cost you in the future. This is a fairly dramatic example of that. This air valve stub on a pipeline was wrapped with a bituminous felt used for waterproofing instead of the coating system that was specified for the pipe. The net result was 100,000 Rand excavation in order to repair it. I think that says it all. Thank you.
Thanks, Neil. That's fairly eye-opening as to the impact of our material selection. As a first question, just to say, there's such a bewildering choice of materials, both for construction, for anodes, for coatings. How on earth do I choose?
You could go back to that comment I made during the presentation on hiring a professional versus hiring an amateur. And there are many people around who have got experience in corrosion and metallurgy, in coatings, in stainless steels, in copper. They've got experience in the operation of plant because they've been operating, say, for example, in the Department of Water Affairs, their engineers have been operating plants for decades. They know what works and they know what doesn't work. There's no one person that knows everything. I mean, yeah, I might have experience in metallurgy and corrosion protection, but don't give the water treatment problem to solve. I will phone up a friend. Don't be scared to ask for questions. Go to people that know, and perhaps go to many people that know, rather than relying on the input from one particular person who may have their own solution. And that may not be the best solution, not because they are deliberately trying to mislead you, but because they perhaps are not aware of what all is available.
I think you've certainly given us some food for thought, and thank you for that. I think we do sometimes feel that we all need to be experts in everything, and we forget the value of mentoring and training those who are coming up beneath us and learning from those who've got many years of experience under their belt. And I think that's always something that we should be reminding ourselves of. I guess to end off this afternoon is just to say thank you to everybody who has joined in, and I hope that you found some of the information that Neil has shared of interest, value. Maybe it's just reminded you that we need to be thinking about these things. And with that, just before I sign off, just to say, if you've got any interest in cathodic protection, or perhaps you want to learn a little bit more, we have just launched our CP101 virtual training course, which is available online. Thank you so much for joining us. Have a wonderful rest of the day. Thank you.